Okay. Hi, everyone. So I'm very happy to introduce Haroon Anwar. He's been working with Sam Nimutin as a research scientist at the Nathan Klein Institute for Psychiatric Disease, for psychiatric research. And he's been working on this very interesting project trying to train detailed psychic networks to learn to play Atari games, a very hot topic in machine learning, but he's trying to do it with spiking networks and see the advantages of that. Haroon, before that, was at Princeton University doing a postdoc, and we're very happy to have Haroon today. Thank you so much for giving this talk.
Thank you for inviting me to give this talk. So I think it's very interesting time to do this all virtually. So it's a new experience, but it's fun too. So okay, so today I'm going to talk about reinforcement learning and some biophysical detailed models and some games. So we live in very interesting time, as I think that all of us are aware that there is quite some time to do artificial intelligence. But whenever we talk about artificial intelligence, we have to remember where does it come from. Of course, a lot of work is kind of inspired from biological intelligence. So it's important to understand where we stand. So I will just quickly go through these some positive, some pros and cons of biological intelligence versus artificial intelligence. Some people may agree, some people don't, but I think this way. So one thing about biological systems is that animals or any system which is biological, it quickly learns as compared to artificial intelligence, where there's a slow learning. So it takes a lot of time, repetitions, to learn the behavior. The second point that I think about biological intelligence is that it's broad. I mean, it's not tuned to deal with a particular task. But then the problem is that it's suboptimal. As everyone can see, that the performance of individuals is it depends on many factors. On the other hand, artificial intelligence, it's great because I mean you can train the models to perform amazingly great, and those systems can really beat even human intelligence. But the problem is that the trained models are very limited in the capacity in terms that they can only play what they have learned about. So again, the next point is that biological intelligence, I mean, there is unlimited capacity. One could argue that that's not true, but again, I mean, all our life we learn one task to another task, and pretty much we remember those tasks and how to perform under different conditions throughout our life. However, in artificial intelligence, I mean, there's a limited capacity because everything is stored in limited amount of synapses or whatever you call. Then there is a chance that when you try to learn a new task, then you start forgetting what you learned earlier. So the other point is that humans especially can actually perform very well in unforeseen situations, whereas artificial intelligence or deep learning models, they fail in unforeseen situations. They need data to base their decisions on. Without that, they cannot decide what to do. So these are just the main points. So the goal of neuroscience community is to understand the mechanisms underlying biological intelligence. And the goal of computer scientists is to improve AI models to include all missing capabilities of biological intelligence. So if we look at the state of the art deep learning models. And so, I mean, I talk quite often with my friends, with my class fellows. So when I was in undergrad, that was like 2000, 2004. Um, we were learning all these artificial neural networks, and pretty much most of the models are very, very similar. But it's only recently that this theme, the deep learning models, became very popular. And one of the reason of its limited use in the past was limited data availability, as well as the limited computational ability. And if we look at this paper, I just got it from arXiv, and then they talk about some limitation of deep learning, that it is somewhat limited by the computational power. So after saying that, it doesn't mean that the computational neuroscience models are better. We are also facing the same challenges. However, there are some insights that can only be learned using biophysically detailed models. So then I think everybody knows about this DQN model, which performs extremely well playing Atari games, and even better than humans. And but a bunch of issues from biological perspective are that the neurons are very simple as compared to the biological neurons. Um, Circuits are mainly feed forward. Of course, I mean, a lot of work is also being done now with the recurrent connections and everything. And the learning is in a way which is very, very unbiological. Like, I mean, the whole episode is repeated and all the weights are calculated. And then you go back in time to see what action caused what problem, what error, and how much did that contribute. And then you make the changes in the connections or synaptic weights so that the model can learn about how to perform in a particular condition. Then there is some work which is kind of a hybrid in nature, that people trained artificial neural networks and then converted into spiking neural networks to see that if they can get some insight. And then when they did that, there was some degradation in performance, but overall they were very successful. But still, we don't know that what's the next step in this kind of approach, whether they can extend it further to understand anything about the biological intelligence or not. Then, so what our motivation is that we want to use more realistic microcircuits and neurons to provide insight into biological dynamics and how those mechanisms contribute to the function. And then, as I said earlier, that we want to provide some lessons for engineers and for computer scientists so that they can really improve their deep learning models to overcome all the limitations that exist right now. And we think that as all AI community is working with games, I think it's a good platform to test all the models. And so that's why we also decided to use games to study multi-scale circuit dynamics and their role in learning and behavior. So before I jump to the work that I'm doing with Sam, I will just briefly cover two models. Okay, before models even. So one thing that humans have, that we have learned over past decades, even more than that, is that uh, it's a very neat framework that to learn anything, if you can associate the learning with a reward, then you can actually track how much you can track the learning. So this was proposed by a neuroscientist, Izikevich, in 2008. And the concept of reinforcement learning is pretty old, but what he did was how to implement that. So he provided this theoretical model, which allows integration of action and reward with the activity, which is basically with the sensory activity. So this is a very simplified model, as you can see on my screen, that we have on the upper, on above here, we see that there is a presynaptic spiking activity, and then there is a postsynaptic spiking activity. So this is a standard STDP rule that whenever presynaptic and postsynaptic neurons spike within a very short duration, then they become then they can be reinforced, or they can increase this in strength of the synaptic weight. So what we are doing is that using the same framework, and we say that, okay, if the presynaptic spike occurs before postsynaptic spike, then we say that this uh, coupled neuron pair will have some effect in distant future. So to track that, what we do is that we activate an eligibility trace uh, that you can see in blue. And after it becomes activated, then it starts decaying. So whenever there is a reward or punishment coming in, we can make association of this reward or punishment to the pair of neurons using this eligibility trace, as you can see indicated by the green arrow dashed line and the red dashed line. So what happens to the synaptic strength? That whenever there is a reward, there is an increase in the synaptic strength, which means that it says that this pair had a positive contribution towards the action, which caused a reward generation. And when there is a punishment, then we reduce the synaptic strength, which somehow encode the concept of punishment to the pair of neurons. So this is the general framework that people have been using very, very commonly. Two examples that I will talk about. One is from Salvador, uh, and I think he can talk better about this model. But they had this motor cortex spinal cord model that they trained to control the arm model and robot arm at the same time in different papers, and you can see that they have a fixed target, and the model learns by making different errors how to optimize its way to reach the target. And they very successfully did that they tried for different positions, and the model learns very well using reinforcement learning paradigm that I just talked in the previous slide. So another example is from Bazenov lab. This is a bit more recent paper where they try to implement the foraging task, that how we can navigate the environment to get to the fixed position where the reward is or the food is. And then they use the similar kind of technique using the STDP reinforcement learning with a different and more simple network architecture. So the point is only that for these both examples, as you can see here, that when it's untrained, and then it doesn't know where the food is, but later it's nicely tracking the food particles in the arena. Um, so these models are learning nicely. So nobody compared the performance with the deep learning model. I guess that deep learning models are gonna do superior job in this task too. There is no doubt about that. However, as I mentioned earlier, that the point is not only to have models, computational models, which can perform better than deep learning models, but it's also to give us biological insights. What are the limiting factors which are causing forgetting and those kind of things? So these models, once developed further, can be used to guide something to the deep learning community too. Um, So, but one thing that I want to point here is that most of the time during these two training sessions, training models, the target was fixed, and it was not continuously changing, as it happens in more complex tasks like playing games. So if we look at more complex behaviors, there actually you need to have a system where it can um, it can transform sensory motor information and associate the sensory motor information to different reward paradigms. So this is just a small summary, like a design that we had before we started the project. And at that time, we thought that we will use the Pong environment. So you can see that if we have a Pong environment where there are like two players which are playing the Pong game, then if we have to train a model to learn how to play this game, then we need to provide some information about the environment to the model. As you can see, it's going topographic visual input to the thalamus and to the visual cortex. And through direct and indirect pathways, it activates motor cortex. And the motor cortex produce an action that is fed back to the game environment. So when that action is executed, then there is a reward or punishment associated to that, to not only to that one action, but a sequence of actions, because the reward and the punishment is only delivered when one of the players wins or loses the serve. So this is pretty complex task that we do not we do not realize early, but believe me, this is really like complicated task to train the model with. So we are going to do is that we will have we decided to simplify the game, and instead of having two players because it was making our life difficult, we not only had to have track the self motion but also track the moves of the other player, which were controlled by the computer. So what we did that we reduced the game, and what we had only one racket or paddle, and the ball was moving, bouncing around in the court, and the task was that this paddle had to hit the ball. So if it hits the ball, then it gets a reward. If it missed the ball, it gets punishment. That's simply the game. And we designed this architecture for the model to play the game. So again, like as I showed you in previous schematic diagram, that the game is basically producing different image frames which give us information about the about the environment. And also using two image frames, we can compute the motion fields of the movement of which tells us about the movement of the ball, that in which direction the ball is moving, as well as the movement of the racket. And then we feed all these two informations, like the location and the direction of motion, to the visual cortex neurons. So how we model the visual cortex, you can see here, I have put this in this format. So all these neurons belong to visual cortex. I mean, again, this is not representing the real, like the cortical structure of the visual cortex. We have some representation of neurons in the visual cortex that can sufficiently encode both location and the direction of objects in the visual environment. And there are some details. For example, the neurons that we are using here are integrate and fire models, because we wanted these models to be efficient computationally. We are using both excitatory and inhibitory synapses, using AMPA, NMDA, and GABAergic dynamics. And then what happens is that after this visual cortex, the neurons are driven in visual cortex. They provide input in a feed forward fashion to association cortex. Because why we are using these association cortices? Because the racket has to know not only about the ball but also about itself. So there are multiple cues which needs to be integrated in some brain area, and then we just basically call it association cortex. In real brain, this could be happening in very large population of neurons distributed across different cortices. But just for the sake of simplicity, we are limiting us to only, we call it association cortices, EA and EA2. And all these the circles are basically representing the neurons, and I'm just showing red to show that any activity in the visual cortex will activate neurons in association cortices EA and EA2, which in turn will drive the neurons in the motor cortex. So we also, again, we do not have a complicated model of motor cortex as Selva had in his arm model. We had much simpler model where we have a population of neurons controlling the move up motion, and other population which is controlling the move down motion. And then there are some inhibitory neurons which can actually control the population activity and stopping them to get into the hyper activity regime. So this model I call still a feed forward model. This is again not accurate representation of the biological model. However, this is the first step that we have, and then we keep these synaptic connections from association cortices to motor cortex. You can see here with the P label. These synaptic connections, we keep them as plastic, which means that once we start simulating the model to train about the behavior, then these synaptic connections will change its weight based on the reinforcement learning paradigm that we use. Okay, so as I mentioned earlier, that we have two kinds of reward coming out of the game. When the model is scoring a point, or when the model is losing a point. So if we look at how many steps it takes from one side of the court to get to the racket, it's roughly about 60 to 70 steps. So which means that the model has to generate 60 to 70 actions from motor cortex to get to a point where it can receive a reward or punishment. Okay, so that's a long time. So we have two options here. Either we use a distal reward learning paradigm, or we do another trick that I'm gonna talk about here, that is using the intermediate reward. So what are the intermediate rewards? We have somehow this ability to predict that where the ball is going to land. Okay, and based on that, we can make an action which will move us towards the target, or we can make an action which will move us away from the target. So all those individual actions can now be associated with individual intermediate rewards, or I can say instantaneous rewards. Okay, so for example, in this case, in the upper panel, you can see that the prediction is that the ball is gonna come to this point, this pixel, which is indicated by the red dot, and the racket is here. So the proposed action is that the racket should move up. Now, if the racket moves up towards the predicted location of the ball, then it will receive a small reward. If it moves away, then it will receive a small punishment. So this is different than the actual reward and punishment. And then we are going to use these small intermediate rewards to train our model. So there are some plus and negative, pros and cons of using these different paradigms. If we use the distal rewards, then we will have infrequent reward signals, mean that the training will take much longer time. However, if we have intermediate reward, then it will allow us to learn faster. And but but we don't know exactly that which strategy would be more successful at this point. And we assume that combining these two approaches could yield better performance. So we will see that what comes out of this. So again, I'm going to repeat, there is a little bit of repetition here. So this is the case of distal reward, that in distal reward, all the synapses um, are are eligible for eligibility trace activation. Okay, so which is different than when I'm using the instantaneous rewards. In an instantaneous reward, only the synaptic connections between association layer and the cortex, which produce the action, will be available for the reinforcement learning. As you can see that if the action is move up, only the connections between A and up will be eligible for eligibility trace. If the action is moved down, then only these connections will be eligible uh, for strengthening or weakening. So we use this technique, and when I train the network, so the network has, as you can see here, my network has more than 12,000 neurons, and this is the raster plot for a very short duration of time during the training, just to show you that how different neurons in different areas are active and what are the firing rates of those. So this can allow us to dig deep into the dynamics of the network, but I'm not going to do right now that part. So you can also see that after the training that the weights of the synaptic connections, these are the average weights. So over a long period of time, the weight of synaptic connections go up. So similarly, the firing rate also of both EM down and EM up neurons also go up. This is just showing that we can have an access to more internal dynamics of the model so that we can learn what's going wrong and can improve those models. So this is the performance during training. So what I did that I just wanted to see how many hits versus how many miss the model is doing over a learning period. And you can see that when the first time I was training the model, the ratio between hit and miss was pretty low. But as we train for again and again over several training episodes, the performance is going up and up. So this is not the end. We can train it further, but just for the simplicity, I'm keeping it until this point. Similarly, you can see as on the left side that a number of miss are going down and number of hits are going up. And this is the data point that I'm going to talk about in the next slide. So the other issue, the other thing is that we want to see that how different ball trajectories, how the model is learning about different ball trajectories. And there I want to make this point that that the model has a different performance for different ball trajectories. As you can see, I don't know if how clear this is, but I'm going to just move my pointer that in this sequence of ball trajectory, the ball is moving from here, it bounced from here, it went up, bounced again, went down, bounced again, and then came up here. This one, it started from the middle of the court wall, it bounced from the middle of the court, and then went again up towards the midpoint. This is a different sequence, and this is the different sequence. So these are, this is the post simulation analysis. I went back and I looked at different input sequences to see that if I track the ball trajectory, how the model is learning about individual ball trajectories. And you can see, looking at these hit-miss ratios, that it's learning very different for different type of inputs. For example, for this one, when this pattern happened for the 15th time, only then the model didn't hit the ball. Um, and then it started decreasing the performance. So one thing is that so there are a couple of points here. Let's first talk about other input sequences. So what's happening here is that the model start learning how to hit the ball, until this point, and then it's again start decreasing, which means that it start forgetting how to hit the ball. So this sequence was repeated more than 150 times. For this sequence, you see that it never missed the ball, even for the first time when it encountered that particular sequence. So there are several messages here. One is that some performance is innate to the architecture of the network. So I believe that this is not a learned behavior, probably because the first time it encountered the ball, it hit the ball, and it kept hitting the ball all the time. However, if we look at this sequence, that even after trying 26 times, it never hit the ball. So, which means that there is some limitation in the circuit which cannot allow the model to learn how to pick the ball, how to hit the ball. Okay, so this is all happening during the training. We can also learn before and after training, which means that now I'm going to turn off the plasticity in the model, and I can again play the game with the learned synaptic connections. So this is the example that I showed even in here with the circle, that this showed the best performance around 0.92. And now what I'm going to do is that for 0.94, for these synaptic connections, I'm going to play a game again and see how the model is performing. Now I cannot forget about anything. I cannot learn about new patterns. It's fixed. It can just allow me to evaluate the performance. And at the same time, I also ran my simulations before training, which was using the initial weights, so that I can see whether my model learned anything or not, or is it just random activity going on. So you can see that before training, the performance was around 0.35. And after training, the performance was around 0.89, average of these endpoints. So this is the performance. It's not one-to-one comparison, but this is because this is a dynamically changing situation. If the model hits the ball, then the next sequence is going to be different between two simulations. But this is just to give you an idea that what's happening during the game, that there are different input sequences coming in, and the model is behaving based on its fixed synaptic connections. So this is left is before training and right is after training that you saw in the previous video. I'll just keep it running for just 1 minute. Okay, I think we can move on. I mean, these are pretty movies to watch, but yeah, okay. So you see, the speed is also changing dynamically. So it's a really interesting aspect of the game that it's still learning how to pick the ball. Okay, so I'm gonna go to the next slide. Okay, so then the other test, I mean, this is the video. It's very hard to compare sequence by sequence. So what I did, that I also analyzed different ball trajectories. So I'm just going to show you here two ball trajectories. One starting from ball trajectory, one starting from pixel height 40, it going down and then bouncing back. And then the second ball trajectory is it's starting from a bit up 20, it going to 60 and then bouncing back. And then I'm comparing, the left column is showing before training, and the right column is showing after training. And I think I don't have to tell you, looking at these ratios, you can clearly tell that there is a clear learning. And the model after learning, after 18 episodes of training, the model is doing a reasonable job. I mean, it's not going to be deep learning model because we have only done 18 training episodes as compared to thousands of training episodes for those models. But but I think that this is basically a proof of concept that these models can learn those things. This is the summary of all the input sequences which were encountered before training and after training, episode 18. And you can clearly see that I'm plotting the median and max of hit versus miss. And you can clearly see that after training, the performance of learning about all different sequences is quite high now. Okay. So now, what about does the performance depend on the ball's spatial trajectory? Because we notice that there is something weird about the model, that it's unable to learn some specific patterns. So we wanted to dig further and wanted to see that whether it has anything that if the ball is moving toward the corner, then it might be difficult for the model to pick it up or to estimate where it is going to land or something like that. So what we are doing here is basically analyzing that part. And you see here that on x-axis is ball y position when it is going to cross the racket. And you can see that the blue are hits and the red are miss. And you can see that after learning, it has learned quite much how to hit the ball when the ball is coming towards the center of the court. Okay. And definitely it has learned a little bit more about how to hit the ball on the corners, but not as much as in the center. So this is some limitation of the model we still do not understand how to overcome in our model. It might have something to do with the architecture or with the boundary effect, or we don't know yet. Okay. So the other thing is that this spike time dependent plasticity is a bit, it has some inherent limitation that if, because it's a feed forward driven model, so if the postsynaptic neuron is not firing, then there are very little chances that the synapse between pre and post is ever going to become activated. Okay. Because either we have to drive the postsynaptic neuron with some kind of a noise, which can allow some kind of exploration of space. I'm talking about the motor neurons. Okay. So I wanted to check whether there is some kind of effect of initial dynamics on the performance of the model. And what I did, that I looked at how different neurons in the motor cortex are performing or are contributing in action generation before training and after training. And you can see that if it was just a linear bump, a full linear bump, then I would say that this is very much dependent on the initial dynamics. But you can see that around the mean or average line, there is quite some fluctuation, which means that the model is exploring the motor actions quite nicely around the mean value. The other thing that this model allows us is to see how many neurons are taking part in action generation. So what I did, that I looked at all actions which were produced and look at how many neurons were active during how many actions. So this is what it's showing. And we see that in the beginning, either up, this is for the up motor cortex, and this is for the down motor cortex, that about 70% of neurons were silent um, during action generation. However, after learning, now we have less than 60% neuron silence. So it means that more and more neurons are being recruited to cover the motor space. And if we look at the combined population of both EM up and EM down, then it shows that at any time there were only 18% of neurons which were silent all the time during any action generation. Um, so this is just showing that analyzing the data from these models, we can learn about different dynamics of the network, and then use these dynamics to compare our model against the biological models, and then we can actually retune our models to learn something about what is missing from the biological system that can help us improve the models. So, as I talked earlier, that all the work that I have showed you today is feed-forward model. And we know that I talked in the beginning that this is kind of a limitation, that the biological networks are recurrent models, recurrent networks. And there is a lot of recurrent connections and feedback connections in those systems. So what happens if we model those biological details in the model? And that's what we did next. We included all well, as many as biological details about the connectivity in the model, and allowed plasticity in many more connections to see how the model is going to learn about the rewards. And at the same time, we limited ourselves now to the sparse and distal rewards. So here is the list of changes that I included. That I included also inhibitory neurons in every layer, because now I have a more flexible system, more plastic system. So I need to have inhibitory neurons there, which can control the hyperexcitability of the network. I also added recurrent connections, feedback connections from motor cortex to visual areas and to association areas, and then used eligibility traces with long time constant, order of seconds, so that it can only allow integration of win or lose or hit or miss for this model. And I'm just showing you one example that this performance was achieved at the end of training episode 31. So you see, if you remember that I had a pretty like 0.94 performance after episode 18 when I was using intermediate rewards. And here I got similar performance after 50% more training episodes. So this was basically our hypothesis too, that in the beginning, that we will need intermediate rewards or instantaneous rewards to speed up the learning. Okay. However, so there are quite a few things that we need to include in this model to improve the performance, to make it compatible with deep learning models. That work is in progress. Okay, so with this, I'm going to conclude that we learned that from these modeling experiments, we learned that closed loop models of sensory motor, visual motor cortex successfully learn behaviors in dynamic environments. So this is the new thing, that having dynamic environment, which was not done earlier, by using spike time dependent reinforcement learning. Then the other thing that I just mentioned also about the sparse infrequent rewards are effective, but intermediate teacher guided rewards accelerate learning. Our models provide potential alternatives to the commonly used deep learning algorithms and additionally offer insight into neurobiological processes. So, this is a really important message that we want to have something which we can use to learn biology too. Then a multi-scale model with biological plausible learning rules can provide mechanistic insight on the origin of dynamics, learning, and behavior originating in the thalamocortical system. And this is ongoing study. We still have to take care of the forgetting behavior in the model. We still need to expand the capacity of the model, and then we need to try how different, like hybrid, kind of a system work in using these models. So hopefully you will learn more about these things next time. Thank you so much. I want to acknowledge the project is primarily funded by Army Research Office and National Institute of Health. And then thanks to Sam for giving me opportunity to work on this project, and then all other team at SUNY Downstate and Tufts and Yale, who helped us with development of NetPyNE, because without NetPyNE, this thing would take much more time. Thank you so much.
Thank you so much, Haroon. Great talk.
You're welcome. You're welcome.
So we'll open it to questions now.
Okay.
Haroon, I have a question, Don. You mentioned you have the you needed to make the model follow the opponent's paddle in addition to its own.
That was, yeah, that would make life difficult, right? So
if it what did you is that you did have it follow the opponents in addition to its own?
no.
Okay.
Yeah, we reduced the model to this is the game, right? So you can see here, right? So there is only one paddle, right? So we took out the opponent, because then to score a point, the model will have to learn the behavior of the opponent too.
Okay.
Right. So which makes things much more uncontrolled for us.
Yes. It might be interesting in the future, kind of like a mirror neuron. And sort of along those lines, I was also thinking about your association cortex, which, have you seen any potential similarity to premotor kind of cortices?
No, I mean, I hope that I know what kind of activity in premotor cortex to expect to compare it with. Right. I mean, but I haven't looked at it from that point of view yet.
Okay. No, it's just very interesting. Thank you.
Yeah. You're welcome. Any more questions?
Okay, so let's thank Haroon again. Thank you so much for your talk. It was great to have you here.
Thank you. Yeah, if you have any question, I will join Slack too, or you can send me email or anything. If anything unclear, don't be afraid to ask questions. I mean, we all are here to learn. So
Great.
yeah.
So you'll have access to Haroon through Slack as well.
Yeah. Thank you.
Thank you so much.
Yeah. Have a good evening.
Thank you.
You too.
Bye.
Thank you very much.
Welcome.